Hey guys, we're back, and this is the last section that we're going to cover in chapter 9, estimating the value of a parameter. And the lesson that we're going to do is standard deviation. Remember, we could do standard deviation and variance in the same thing, because variance is just standard deviation squared. All right, so with population, so p hat looking for p, we use the normal distribution. With x bar looking for the mean, population mean mu, we use the student's t distribution. And now for standard deviation and variance, we're using wrong one. So for S to our sigma, we're using this new one, chi-square distribution. So chi-squared distribution. All right, let's continue. So for chi-square distribution, if a simple random sample of size n is obtained from a normally distributed population with the mean mu, standard deviation sigma, then chi-squared is equal to our degrees of freedom times our standard deviation squared, or our sample variance divided by our population variance. And this is a chi-square distribution with n-1 degrees of freedom. And characteristics of the chi-square distribution. So this one is different from the standard, from the normal distribution and from the student's t distribution. For this one, it's not symmetrical. So what it looks like is we have like our graph here. It starts right here at 0, pops up, and then comes down this way. So it looks like this. It doesn't look like your normal standard deviation or your normal distribution or even your t-squared distribution. So the area is, or the values are always going to be positive because we start over here at 0 and this keeps going on to infinity. But we have that. All of the values are going to be positive. The area under the curve, or let's just continue on with what they have here. So the shape of the chi-square distribution depends on the degrees of freedom, just like the student's t distribution. So degrees of freedom, some of them are going to look like this. Others are going to look a little bit more different, something a little bit more normal like this. It just depends on what the degrees of freedom are on this one. As the number of degrees of freedom increase, the chi-square distribution becomes more nearly symmetric. So we could check out the figure in the next slide. The values of chi-square are non-negative, so greater than or equal to 0. And this is what we're looking at. So with 2 degrees of freedom, we have this graph right here in blue. With 5 degrees of freedom, notice that all of them start here at 0. They pop up and then come back down. It's infinite on the right tail. Same thing here. So it looks like it doesn't come from 0, but it does come from 0. Same thing here. But the larger you get, the more normal it looks, and normal as in like bell-shaped. So it gets roughly bell-shaped once we have degrees of freedom greater than or equal to 30, roughly. Next, find the critical values that separate the middle 90% of the chi-square distribution from the 5% area on each tail, assuming 15 degrees of freedom. Okay, so what we're going to do is look at those two areas. So we first have this here. We have our 90% here in the middle, or we could think of this as 0.90, which means these two share that 10%, which means the left side is going to have 5%, the right side is going to have 5%. So 0.05 here, 0.05 over here as well. All right, so now we have that. We have our 15 degrees of freedom. So degrees of freedom is equal to 15. And let's see what we have. All right, so okay, so what we're going to do is kind of draw everything from here. what we have is this value right here. We could consider this chi-squared. Let's see. Chi-squared of alpha over 2. So remember, alpha is all the data that we don't have in the middle. So this is going to be alpha over 2. This is going to be chi-squared of 1 minus alpha over 2. So here with this one, the area that we have to the left is going to be that 0.05. So for the first one, for chi-squared left, you could say left. The left one, that's going to be equal to the area here. So we have chi-squared, CHI. So chi-squared distribution or chi-squared inverse, do we need an area for that associated value or do we have an area? So we have an area that we need to get the associated value for. So here probability is going to be the area. So that's going to be 0.05. And our degrees of freedom is going to be 15. So 15 degrees of freedom. That's our chi-squared left value. I'm looking at this, it's just like the left one versus the right one. So that's our chi-squared left value. And now we go for our chi-squared right value. So for the right value, it's going to be this area over here. So remember, we're always looking at the area to the left. So from 0 all the way up to this point here, we have 0.05 plus 0.9. So here the area is going to be 0.95. So equal to a chi-square distribution. So chi-square distribution or chi-squared inverse, do we need an area or do we have an area? In this case, we have an area 0.95. Degrees of freedom, we said we're 15. And there we go. So we have our left value versus our right value. So the smaller value versus the larger value. Remember, the smaller value is going to be on the left side because it's closer to 0. Remember, this comes from a graph that looks something like this. This being 0, our smaller value here, larger value over here on the right side. And that's it there. Let's see if we missed anything. So here we drew our beautiful pictures. So the figure chi-square distribution, 50 degrees of freedom. And the known critical values are labeled. So we said that this left value over here versus this right value over here, middle area is 0.90. And from there, they found it on the table. We use Excel, much more accurate. And next, construct and interpret a confidence interval for the population variance and standard deviation. So remember, variance is sigma squared. Standard deviation is just sigma. So if we were to look at variance to get standard deviation, we would do that. Or to get variance, we would square these values to get back over there. All right, so construct and interpret confidence interval. All right, so a 1 minus alpha times 100% confidence interval for our standard deviation or for our variance. So if a simple random sample of size n is taken from a normal population with a mean mu standard deviation sigma, then a 1 minus alpha times 100% confidence interval for our variance is given by this. So our degrees of freedom times our standard deviation. For the lower bound, we're dividing by 1 minus alpha. For our upper bound, or I'm sorry, we're dividing by chi-squared of alpha over 2. For our upper bound, we have our degrees of freedom times our standard deviation divided by 1 minus alpha over 2. And we're using n minus 1 degrees of freedom. All right, so to find a 1 minus alpha over 2 confidence interval about standard deviation, take the square root of the lower bound and the upper bound. So kind of looking back at this, if we were to take the square root here and the square root here, because what we have is our value here less than or equal to our variance, less than or equal to the other value. Simply taking the square root of all three would get us our standard deviation from here down to here. So that's all this right here is saying. All right, looking at this, table 4 shows the sales price of 12 randomly selected 6-year-old Chevy Corvettes construct a 90% confidence interval for the population variance and standard deviation of the price of a 6-year-old Chevy Corvette. Oh, and I think this is the data that we had last time that we kind of had a mistake on. All right, so from here, take a snapshot. We could go right over here to Excel. So coming over this way, insert data from picture, picture from file, and screenshot. And it looks like the data is skewed a little bit, so I'm going to fix this off camera and I'll be right back. Okay, so now that we have this here, let's grab our necessary information. So again, the values that we're looking at are sigma squared is equal to our degrees of freedom, S squared over chi squared. And now we just need those values. Okay, so sigma squared is what we need. N minus 1 are degrees of freedom. So we could do N. And this is what I was trying to do earlier. N equal to, this is a shortcut just to get you what N is, just based off the data here. So we're going to say count, C-O-U-N-T, and highlight the data. And it's going to tell us how many different values we have here. So we have 12 different values here. This is our degrees of freedom is equal to N minus 1. And we have that. So now we have N minus 1. We need S squared. So let's look for our standard deviation. Standard deviation is going to be equal to ST/DEV of the sample. And just take the standard deviation of this sample. Cool. Chi squared. So now we need our chi squared left and chi squared right. So one thing I forgot to get over here was our confidence interval. So we need a 90% confidence interval. So confidence is 90%. Stretch this out so we get the full word. Okay. So with that, we could find our chi squared left, chi squared right. Okay. So again, we have our degrees of freedom, or we have our data. We want 90% of it to be here in the middle, so 0.9 here, which means that these two are going to share 10%, which means this left side is going to be 0.05. This right side is going to be 0.05 as well. And now to figure out which value we need, this one here is going to be chi squared of 0.05. This one over here is going to be chi squared of 1 minus alpha over 2. So alpha was 1. Another way you could do that one there to find that computation, but this is 0.95 here for this value because we were adding those two different areas together. And now we'll find those two. So we have chi squared left, which is going to be this value here. Chi squared left is going to be equal to chi-square distribution. So do we need chi-square distribution or chi-squared inverse? Do we need an area or do we have an area? In this case, we have an area that we need to find the chi-squared value for. Probability is the area. So for this first one, the left one is going to be 0.05. Degrees of freedom is 11, or we could just click on that button there. And that's our chi squared left, chi squared right. That's going to be equal to, again, chi squared distribution, chi squared distribution, chi squared inverse. We have an area, so it's going to be this one. The probability is going to be the area, 0.95. Degrees of freedom is 11, or we could just click that button. And we have those two. So now that we have that, we could get our lower bound and our upper bound. So similar to the way we would find them before, this time, what we're going to do is divide the two. So we're going to use these values right here to figure out what the lower bound is and what the upper bound is. All right, so now for the lower bound, what we're going to do is divide by the larger number. So we're going to divide by chi-squared right. So equal to our numerator versus denominator. So the numerator is our degrees of freedom times s squared. So we could actually, let's just fix this here. Let's get s squared here. So I should have fixed this part. S, we'll say s squared. This is going to be equal to this value squared. All right, there we go. So now our lower bound, again, lower, we're always going to divide. For a smaller number, you're dividing by a larger number. So this one, we're going to divide by chi-squared right. So this is equal to our numerator versus denominator. So the numerator is our degrees of freedom times s squared. Close the parentheses for the numerator, divided by the denominator, and denominator is going to be this value here. That's our lower, and now we're going to go for our upper. So again, equal to numerator, our degrees of freedom, times s squared. Close parentheses for the numerator, and we're dividing that by the denominator, this time by a smaller number to get the larger value. And there we go. So we have those two values there. This is for the variance. And let's check out what they got for variance. So here, sample standard deviation. We got this value here, 26,115, 26,115, perfect. Sample variance is going to be 26,115 squared. And now because we want a 90% confidence interval, we have 1 minus 0.90, so 10%. So they use this to find our chi-squared right, that's the right value. And our chi-squared left, the left value, the smaller one. And from there, we found our lower bound. So 3.8 million, 3.8 million, yep. And the lower bound or the upper bound was 16.4 million, 16.4 million too. All right, so this is for the variance. So the lower bound for the variance is this right here. And now to find the lower bound and the upper bound for the standard deviation, we would just have to take the square root of it. So again, this is for variance. And this is for a standard deviation. So this is equal to square root of this value here. And same thing here, square root of this value here. And there we go, that's what we have. So just so we could illustrate it in like in a inequality, for variance, we have 3, 8, 2, 3, 6, 7, 1.4, and 3, 3. We have less than or equal to the sample or the population variance, which is less than or equal to the other number, 16444, 663.3 here and here. And now in order to get our standard deviation, we're just going to take the square root of everything, which is what we did here. We took the square root, SQRT. And we're gonna do the same thing over here. So the values that we ended up getting when we took the square root was 1,955.42 less than or equal to our standard deviation, not our variance, just our standard deviation, less than or equal to 4,055.2. And that's what we got here. So this would be for our standard deviation. This is for our variance. And those are the values that they got here too. Here they used StatCrunch. And lastly, interpret the interpretation. So we are 90% confident that the population standard deviation of the price of all 6-year-old Chevy Corvettes is between $1,955 and $4,505 or $4,055. And there's the end of the slideshow. So that wraps up chapter 9. If you guys have any questions, please let me know as soon as possible. Email me. And if not, good luck on your homework. Bye.